My name is Nikos Tsikoudis. I'm a software engineer with Datometry. It's a startup based in San Francisco, California. And Marc, Sugiyama, and I, with this talk, would like to share our experiences and our some lessons we learned while troubleshooting the performance of a large Erlang system. I will start by introducing Datometry and the main product called HyperQ. HyperQ implements a database virtualization. At a high level, it allows applications that are written to run in on a specific type of database to run on a different type of a database. In particular, currently we allow applications that are written to run on a Teradata system to run on a cloud data warehouse, such as Microsoft Azure or Google BigQuery. To achieve this, HyperQ needs to do a couple of things. First, we need to parse, bind, and transform the incoming SQL statements into a SQL dialect that the target database recognizes. And the second thing we do is to fetch the results from the target database, and then we have to convert the result into the format that the source application expects or it can recognize. And then we transfer the result back to the source application. Obviously, having to do this query translation and result conversion introduces some overhead in the query processing time, and in this overhead is where we found some challenges, some performance challenges. HyperQ is implemented entirely in Erlang. It consists of more than 1,000 modules and 2 million lines of code. For this work, we used an actual customer incident where we observed some significant performance overhead processing their queries. It's a large retail organization, and they often impose some strict SLAs when they generate some reports. And the reports they typically generate are based on some SQL select statements that return a very large amount of data. One query that we worked with in this case returned 16 million rows, 20 columns per row. And what we observed for this query is that it used to take 1 minute to execute on the target database, and it took 4 minutes longer for HyperQ to do the query translation, the result conversion, and transfer the result back to the client. So we typically start this troubleshooting process by creating an in-house reproduction. We try to create an environment that is as close to the customer environment as possible. And at this point, I would like to note that many parts inside HyperQ run in parallel. For example, when we fetch the result back from the target database, we split the result into multiple chunks. We convert them in parallel. It looks like like this. So we fetch the first chunk of data. At time T1, we start converting, and then we immediately after fetch the second chunk of data, and we start the conversion. So when this incident happens, our field engineers typically start by providing more resources to HyperQ. For example, by scaling up the CPU, the number of cores that HyperQ can use. Hopefully, it will increase the degree of parallelism whenever there is some kind of parallelism like that. In this case, the first attempt was to increase the number of cores from 32 to 64, but we observed that the query processing time was improved by only 15%, and the cost, the amount of money we have to pay to the cloud provider was twice as much because we use twice as many cores. For this low improvement, we observed a couple of factors. The first one is hyperthreading. In virtualized environments, the number of the cores we use are virtual cores, and typically the physical cores are less than the virtual cores. And we don't really know if the cloud providers oversubscribe the physical cores. Another factor was some cache congestion we observed in HyperQ because of the Erlang VM oversubscribing some threads of execution. So the first step in the troubleshooting and optimizing process is to identify the dominant cost, the component inside HyperQ that contributes to this overhead the most. The first thing we can do is to instrument the code to get some granular timing information. This is often a very tedious work. Something that we really that really help us is that HyperQ is implemented in a modular way, so it is relatively easy to bypass or to wire off certain operations or certain modules. For example, here's an example where we bypass the result conversion module of the product. And we can do this by pre-computing some result. And then when the HyperQ starts, we can load these results into memory, run a query, fetch the result, and instead of invoking the result conversion, we can bypass this module and transfer the result back to the client. So we did this effort with multiple modules, and we end up observing that the result conversion was the module that was contributing the dominant, was the bottleneck. Not very surprising though. Now the next step is to identify the dominant, the high cost components in an even finer granularity. To do that, we utilized the profilers that are available by Erlang. The profilers, these profiling tools are used to collect information about function traces and execution times. We used all three profilers available. The cprof that reports the function call counts across all processes. The eprof that reports function call counts and the time we spend in the function, and the output is organized by process. And the fprof tool that keeps track of the function calls, and it returns, it reports the callers and the called functions for some subject functions. The profiling phase is typically an iterative process. We need to profile multiple times. Because we typically profile once, we detect high cost components, we optimize them, and then we need to go back to the profiling phase to get a fresh results from the profilers, and hopefully we'll find more components to optimize. And because of that, it's important to define a baseline experiment that is deterministic and easily repeatable. And this would help to be able to compare the multiple iterations to each other. In our case, the baseline experiment was a simple select statement that returns several rows from a table that was pre-created for this process. Our goal during this phase is first to make sure that we get the expected number of function calls. For example, if we have a function that we know we use this function once per row, if the query returns 1 million rows, if the profiler says that, or this function was called 2 million rows, we can probably conclude that there is a bug around this function, and we'll look for that. The second goal and most important is to detect the high-cost components in the product and try to optimize them. So we start with cproof, which, as I said, it returns function call counts. This helps with our first goal, which is to make sure that we have the expected number of function calls. And this is a sample output of cproof when we run it when we used it for HyperQ. And the first column is the number of function calls, and here are some functions. And we observe that do flatten is the function that is most commonly used in HyperQ. So by looking at this report, we can collect some functions that appear very high and flag them as functions of interest for further investigation. Then we move to eproof that reports the function call counts and timings, and it's organized by process. So this is very important to us because we want to focus on processes that participate in the result conversion. As we know, the result conversion is the bottleneck in our system. This is an output of a process that does the result conversion. And as we can see here, we also see the do flatten function being not only the one that is called more often, but also the one we spend most of our time. So now, after running cproof and eproof, we have collected some functions that we would like to investigate. However, we haven't written some of these functions. We haven't written the do flatten. So what can we do about that? We use fproof. Fproof tracks the function calls and returns callers and called functions. The output is organized in sections where one section is here where there is a subject function that is marked by the percentage character. Here we have the do flatten as a subject function. Above is the callers, below are the called functions. We see that the flatten function is one of the callers. So we jump to the section where the flatten function is the subject function, and we see the callers. And now we start see some functions like the format date function here. That is one of the functions that we have written. That's part of HyperQ. So only after we have combined the outputs of all three profilers, we can detect what parts of HyperQ we should be looking at. One part of HyperQ we found out that contributes significant overhead is when we format date values as well as time values and timestamp values. Date, time, and timestamp data types are very commonly used in the database world. And here I have an example where I have a date formatter. This is how the function used to be in HyperQ before an optimization. This function gets two arguments, a format and a date value. First, it calls a helper function that produces a list of pairs of IO_lib formats and some values. Then it calls unzip on this list to separate those, and then it calls flatten on the formats and IO_lib format in order to generate the final result, which is the date formatted based on the given format. So this function was one of the main sources of the do flatten function that got reported by the profilers as being the function that is most commonly used by HyperQ. Fortunately, date formats and time formats and timestamp formats, they are very well defined. For example, we don't have more than 4 digits for the year part or more than 2 digits for the month or the date format. So we came up with a bespoke version of the code of this function, which parses the format, and it appends the values that will consist the final output into a list, and then we return this list. So this function eliminates all the general purpose function that this function was using. It eliminates the unzip, the flatten, the OLID format. And this can be done because we know that the values coming in are well defined. So after doing this refactoring of the function, we would like to test the impact. We tried to format 1 million dates, and we found out that the bespoke version of the function was 16 times faster than the function that was using the general purpose functions. The improvement in the customer query was 20%. And since we were happy with these results, we extended this approach to other data types, such as timestamp and certain numerical data types. So here I would like to share some takeaways from this profiling phase. No conclusions can be confidently drawn by using one profiler alone. So the process that worked for us was to start with cprof and tprof, detect the high-cost functions, then use the fprof to walk through the function calls and find what are the functions we should be optimizing. Only after combining all the profilers, we could easily triangulate the problematic parts of the product. And we also concluded that often a bespoke version of a function can perform significantly better than a function that is using more like a general purpose functions. In the next part of the talk, I would like to share some optimizations that are not easily detected by the profilers by looking at the profiling output. So here, after we study the profiling output, we get an idea of what functions we might want to investigate. But when we look at the code of those functions, it's not easy to understand what is a good implementation versus a bad implementation. And in this case, I will share a couple of optimizations that we came up with while we're trying to optimize our use of binaries. What helped us here was this flag from the Erlang compiler, the bin-opt info flag. So when this is enabled, this reports some warnings about some sort of good news and bad news. Like it reports when an optimization has been applied or an optimization did not get applied, and a hint about what the problem was. After we discovered there are some optimization opportunities here, we start experimenting with simple programs and some simple test harnesses. This is a simple program we wrote, and this kind of simulate many functions that we have in the product. So what it does, it will get like some binary. Typically, it's like a long binary because these binaries are an entire row, part of the SQL response. And then it will. There is some function that will split the binary and decode this binary in small chunks and return those chunks to some other function. So a couple of things that I would like to share is that The first example is that we tried to add pattern matching to all functions where the arguments we know for sure there were binaries. And it's important here that we added the pattern matching in the catch-all function as well. This gave quite a bit of a performance improvement for this particular code, 20%. And it's important. This is the important part. If the binary pattern matching is not added in the catch-all, the compiler is not gonna know that these are binary, and the optimization will go away. The second change we did was that so we have this decode function that splits the binary and does some work that we have omitted here, and then it returns the decoded part and the remainder of the binary. So something we tried here was, instead of returning the remainder, we return the length of the decoded value. And then we have the calling function do the slicing and carry on with the process. And this gave another significant performance improvement, which was 60% for this particular program. So the takeaways that I would like to share from this part is that if the argument of a function is a binary, we suggest using the binary pattern matching, including the catch-all part, and we also suggest avoiding returning the remainder when you split and decode binaries, and instead return the size or the length of the decoded part. And then another change we adopted, but didn't give as much of a performance improvement, was to replace guards that use this binary function with binary pattern matching. And I have two more optimizations that I would like to share. We wrote two C-based nifs, and these functions were detected during the profiling phase. The first function calculates the length of a binary, and this replaced several uses of the string length, and the C function performed significantly better than using the string length function. And the second function we wrote is it extracts bits from a binary and creates a list of 0 and 1s. So this list is used during the conversion because it shows where in a single row where the null elements are in a single row. And finally, during this troubleshooting process, we realized that our development environment was using an older GCC version that was not supporting compiling Erlang with JIT, so we made sure to enable that as well. After combining all these optimizations, we wanted to capture the impact. So we used a similar query to the customer's query, which returns 60 million rows and 20 columns, roughly 2 GB of data. HyperQ was running on a 32-core virtual machine, and the improvement, the execution time, the overall execution time through HyperQ was improved by 40%, reduced from 300 seconds to 181 seconds. And this was mainly because the result conversion bottleneck was improved. The result conversion itself was improved more than 50 or 60%, and the result conversion rate increased by 6.3 megabyte per second to 10.5 megabyte per second. And I will conclude this talk with the lessons, the overall lessons that we learned. So, first one is to define a deterministic and easily repeatable baseline experiment. This is important because the profiling and the optimization phase, both of them are like iterative processes. It doesn't happen all at once. So it's important to have an experiment that can be used for each single iteration, and so you can get results that can be compared. The next lesson is that no conclusions can be drawn confidently by using one profiler alone. Next, we realized that often bespoke code performs significantly better than code that relies on general purpose functions. We find out that some small C-based functions that are they can safely replace some Erlang code for better performance. And when it comes to our binary refactorings or optimizations, we suggest using binary pattern matching in function heads whenever the arguments are binaries, including the catch-all. And we suggest avoiding returning the binary reminders from functions, and instead return the length of the decoded part of the binary. And yeah, that's all I have to share with you all, and I'm happy to answer any questions you might have.
Thank you very much.